In Chapter 2, we're going to start looking at probability. So just like in the previous chapter when I said we needed to know the definition of statistics, here we need to know the definition of probability. Now we all have an intuitive idea what probability is, the chance that something might happen, or if we see something happen, the probability that something else might happen after that as a consequence. But I think a really nice definition of probability basically boils down to the chance that an event will occur, I think we can all agree on this. But because we don't want to have that subjective or intuitive probability kind of bringing into play, we are going to base this chance on long-term relative frequency. So the chance that an event will occur based on long-term relative frequency. So basically what this means is we start to look at patterns, we start to see how things occur and don't occur over long term, and then based on what I've observed I try and draw some conclusions. So this is the idea of probability. And again, this is a definition, it'll probably be the second question on your first exam, so make sure you have a good idea of the definition of statistics and the definition of probability. So to get started talking about probability, we need to define some pretty basic ideas. The first idea is to define an experiment. And basically an experiment is any activity or any process that we look at whose outcome is subject to uncertainty. And because it's subject to uncertainty, I have something in an experiment called a variable. So when we talk about a variable, I might talk about blood pressure, or whether you drive a foreign or domestic car. Those would vary from person to person. If I was flipping a coin, the variable would be whether it lands on heads or tails. So once I have an experiment and I'm not sure exactly what some of the outcomes might turn out to be, I have to start talking about a sample space. And what a sample space does is a list of all possible outcomes of an experiment. So for example, if I was talking about flipping a coin, I might list the possible outcomes as heads or tails. Now when we're talking about sample space, we usually denote sample space with the letter S, and then we have a listing, in this case, of heads or tails if I was flipping a coin. If I was talking about the type of car you drove, I could talk about foreign or domestic. If I could talk about possible grades in this class, A, B, C, D, F. We do not use pluses or minuses in South Dakota in the Regental system, so A, B, C, D, F would be the possible sample spaces. So when we talk about the sample spaces, I'm really talking about all the possible outcomes from basically one flip of a coin, asking one person what type of vehicle they drive, or asking one person what possible grades they could have. Now what I need to consider is what if you were to ask more than one person, then the sample space would change. So for instance, let's suppose we asked 3 people to flip a coin. So we have 3 flips of a coin. What are the possible outcomes here? Well, here the sample space changes. With each individual flip, I know it's in either a head or a tail. But if I flip a coin 3 times, I could have head, head, head. I could have head, tail, 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 head, head, etc. And all the way up to tail, tail, tail. And so the sample space would be a complete listing of all these possible outcomes. Now, just as a quick side note, how many possible outcomes should there be here in this sample space? Well, if you think about 3 flips, here's my first, second, and third flip, so first, second, and third flip. There's 2 possible outcomes for the first flip, 2 possible outcomes for the second, and 2 possible outcomes for the third. So if you want to think about it, this is the same as 2 to the third, or 8 possible outcomes. So there should be a listing of 8 possible values here. And it probably would be a bad idea if you took a second to see if you could write them all out. Now from here, within these sample spaces, I start talking about events that can occur. Now there's 2 types of events that can occur. The first type of an event, first of all, is any collection of outcomes contained in the sample space. So any collection of outcomes contained in the sample space. So it's usually some sort of a subset of the sample space. So I have two types of events. I have a simple event and a compound event. So let's go ahead and look at a simple event. A simple event basically consists of exactly one outcome. So you can imagine that a compound event would basically be more than one outcome. Now you might look at the things that we have listed up above and say, okay, everything up here, these must be simple events because there's only, one thing that's occurring here and here. And these must be compound events because of more than one outcome. But really what we need to talk about are such as in this case, the compound event would be, let's say, where can I have two tails occurring? Well, two tails could occur here, or if I wrote out all my other events, they could occur two tails and a head and two tails like we have here, etc. So that's an example of a compound event. So let's go ahead and look at an example where we're actually writing out all the possible events, and then we're looking at some simple and different compound events for those. So for this example, we are going to ask three people, so lowercase n, three people, what type of vehicle they drive, whether it's foreign or domestic. So one thing that could happen is all three people could say foreign. Another thing that could happen is one person could say foreign, and of course the other two would be domestic. Well, I have three people I'm asking though, so this can happen quite a few different ways. Another option here is the first person could have said domestic, the second person foreign, so this could be an option. And of course, as we see this occurring, the last person could have said foreign as well. So this is kind of the case of 2 to the third, which is 8, and I have 1, 2, 3, 4 of the possible outcomes so far. The next thing that could happen is I could have, instead of one foreign, I could have two foreign responses and a domestic. Another way to think about this is just worrying about the one domestic response. And I could look at all three of those cases as well. So I have 3 foreign, 1 foreign, 2 foreign, and I could also go up to no foreign, which would be all domestic. So if I look at the total number of values here in this sample space, I get 8 possible outcomes. And then from here, I can answer all sorts of different types of questions. So we want to keep our sample space in mind. So let's look at one possible question. One possible question might be something like, let's let event A equal the event that exactly 3 people own foreign cars. So that would mean A would equal the outcome foreign, 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 and this would be called a simple event because there's only one possible outcome here. We could look at another example, B, be the event that at least, and the at least is important here, at least 2 people own domestic cars. Okay, so if we were to look at the event B, where at least 2 people own domestic cars, we need to think about that pretty carefully. At least 2 people own domestic cars would be 2 people own domestic plus, or however you want to look at that, 3 people own domestic. Now this is not finding the sample space, this is just kind of writing out what the sample space will be eventually. So 2 people own domestic. Well, if we look up here, 2 people owning domestic are these 3 cases right here. So that would look like FDD, DFD, and DDF. So 2 people own domestic is here. Now 3 people owning domestic would be DDD. And that would be right here. And so we can tell that this is a compound event because basically what we have here, there's more than one possible outcome that would answer this type of question. So important terminologies that are going to come up a lot are things like at least and at most. Now since we brought this up already, let's go ahead and talk about some set theory. Now when we talk about set theory, we're talking about things like the complement of an event. We're talking about the union of events. And we're also talking about intersections of an event, of events. Okay, well, first of all, the complement usually is denoted A prime. Sometimes you'll also see it denoted as AC. Those are different ways that we can use the idea of a complement. And basically, A complement means all of the values that are not contained in A. So we'll write out some Venn diagrams here in a second to show what these look like. Now union we can represent a couple different ways. First of all, when we talk about union, we say ORs. So sometimes you'll see these written as A or B. This is not the letter U. It's a symbol that means union or OR. And basically what we have here for A or B, we're looking at the event consisting of all outcomes that are either in A or in B or in both. So all the outcomes that are either in A or B or both. And of course when we say both here, we're saying both A and B, so for both events. And we'll draw a Venn diagram of that one as well. Now intersection is our AND. So this would be A and B. And basically what we have here, it's the event consisting of all outcomes that are in both A and B. So all the outcomes that are in both A and B. And I'm going to use a Venn diagram to show what some of these look like. So let's look at this first case. So this is A complement or A prime. So if here is event A and here is event B, everything outside of A is what not A makes up. So everything we have shaded here is not A. Now we have to be careful about this spot here where it crosses. If I shaded this area, that would be inside A and B, but importantly it's inside A. So this is a Venn diagram that shows what's happening there. Let's go ahead and look at A or B. So here's our A, here's our B. A or B would be all the events that are in A, all the events that are in B, and of course all the events that are in both A and B. Here's our A or B. So there's A or B. Or I'm sorry, and. We're using and right here. A and B would be the only ones that are common to both event A and B. So again, and. This one is our or, and this is complement. So those are some ideas from set theory that we're going to be using a lot this semester. So it's a good idea to kind of get those understood now so we can try and clarify what they mean, so when we get to more difficult problems it won't be as complicated. Now another important idea that we want to talk about is the idea of events being mutually exclusive. Now another name for mutually exclusive is disjoint. So you'll see the terminologies of mutually exclusive and disjoint being used interchangeably. Now basically mutually exclusive and disjoint is very easily shown by a Venn diagram. So here we have event A and event B. And you'll notice that this is drawn quite a bit differently than these graphs up here. Over here, when I drew events A and B, they crossed each other. They had something in common. But we can see down here for mutually exclusive or disjoint events, A and B have no outcomes in common. So if I have mutually exclusive events, they would be events that have no outcomes in common. So if I talked about an event like a listing of all the even numbers and an event of listing all the odd numbers, they would be mutually exclusive because I would have no one number that occurs in both the even and the odd listing. So this is an idea of what mutually exclusive events look like. Now when you're working a lot of the homework problems from your textbook, a really nice way to try and think about some of these problems is to draw Venn diagrams. Now it's not always going to be possible to draw a Venn diagram because you might have a three-case Venn diagram, you might have an A, B, and a C, and we'll work with one of those in class, but once we get past 3 it's really difficult to work with. So let's go ahead and look at some examples from your text. So this is one of the more difficult examples from this section, and it's basically on page 55, number 9, and we're using this to show DeMorgans Law. Now DeMorgans Law is one that if you get into a lot of set theory you use often. There's actually 2 parts to it, but this one acts as just to verify DeMorgans Law. Now the first part of DeMorgans Law talks about the union of 2 events and then the complement. So it talks about the complement of A or B, and it says to establish that the complement of A or B is equal to not A and not B. Well, we can use a lot of set theory for this, or we can draw some Venn diagrams. So A or B, here's A or B. Now if we were to shade A or B, we would see pretty clearly that it would be this region right here. So this is A or B. Now if we talk about not A or B, it would be this green region outside of this. So not A or B would be in green. Now let's go ahead and have a look over here, and again we're trying to establish this, if this is equal to not A and not B. So here's A and here's B. Now if we talk about not A, we're going to have more than one Venn diagram here. And then we talk about not B and their intersection. Hopefully what I'll do is I'll get the green that we have here on the left hand side. So let's go ahead and look at not A. Not A would be everything outside of A. Not B would be everything outside of B. Now the and part right here would say, you know what, let's go ahead and write down everything that's not common to both of them. Well, first of all, this spot in the middle, this little slice right here, is not common, so I wouldn't include that. This slice over here, this kind of moon-shaped piece over here on the right, is not common to both, so I wouldn't include that. And the same for this moon-shaped piece on the left. So what ends up happening is everything outside. So this shows us that this is a true statement by looking at this green shaded area. So the green shaded area shows us the and, so we can use the Venn diagrams to establish that part of DeMorgans Law. The second part of DeMorgans Law is basically looking at the intersection in the complement. Now we're trying to establish whether this is a true statement, and again we can use ideas from set theory, or we can just go ahead and look at a Venn diagram as well to help us show what's happening here. So again, here we have A, B. Now here I want A and B. So the only thing that's common here to both of these is this little wedge in the middle. So that's A and B. Make that purple so it matches. So that's A and B. Now this says the complement of A and B. So the complement of A and B would be anything outside of there. So that's going to be this shaded or highlighted region outside of that purple. So everything that we have here in red would be A and B not, or complement. Okay, so let's go ahead and look over here, and again what we want to do is we want to look at the right hand side and see if it does indeed equal the left hand side. So here's AB. Notice they are not disjoint. And here we're looking at not A, not B, and the OR. So not A would be everything outside of A. Not B would be everything outside of B. Now the OR would be basically everything that's covered. Now if you note, the only thing that's not covered is this little wedge piece right here on both of these. So if I picked up this left hand side, plopped it down on the right hand side, the only thing that would not be shaded in green is this middle wedge, and we can see that that directly relates to this middle wedge right here as well. So then when we talk about the or, we realize that we're shading all of this red region except for this wedge piece. So again, what we have done is we've established if we lay one of these on top of the other, everything is shaded except, not equal to, that wedge piece, and so this red highlighted area and everything covered by the green will match. So that's an example where you can use DeMorgans to establish that with Venn diagrams. So this is a quick introduction into some basic ideas of probability and some basic terminology of probability before we get into the next section where we start establishing rules and properties of probability.